get started with learning processes. Okay. When we think about learning, what kind of processes do we have for learning? One is learning with a teacher. This is basically supervised learning, and then we have learning without a teacher. There are two steps here. One is unsupervised learning and the other is reinforcement learning. Okay. So, we have unsupervised learning and then we have reinforcement learning. So, if we see through a block diagram what really is happening, then we can appreciate the learning processes. So, let us get started with the first learning mechanism, which is learning with the help of a teacher. We have an environment. We can think about it as a plant or whatever it is in the context of an engineering system, and this environment is giving you some output which goes to a teacher, and you can consider this to be an expert. This is giving you a desired response, and then we have a learning system that has to learn the environment through the desired response given by the teacher. So, the output of the environment is also fed to the learning system. Now, initially to start with, the learning system doesn't know what to produce, but it produces some output, and the teacher, which is an expert, provides a desired response. You formulate an error signal at this step, and this error signal is what you want to minimize, and that drives the adaptation of the learning environment. So, what we mean is the knowledge of the teacher about the environment is directly transferred to the neural network via training, right. So, knowledge of the expert, this case the teacher, about the environment is directly transferred to the neural network via a training procedure, and what happens is the synaptic weights learn the network. I mean the synaptic weights of the network learn the environmental variables. So, this is what really happens, and this is also a basis for error correction learning. Okay. So, the missing details are what is this formulation of the objective function. Now, you have an error signal here, right. You have a desired response and the learning system is producing some response. You take the deviation, you formulate the error metric. What should be your objective of the error, right, and that will kind of influence how the geometry of the problem is in terms of the learning. So, there is the other aspect of learning without a teacher. A good example of learning without a teacher would be social etiquettes. Right, we have some behavior, there is nobody who tells us what needs to be done. We observe the environment and then we learn things, right. So, if this has to be translated into a learning process within a neural network, how do we go about doing this? So, there are two possibilities. One is unsupervised learning, other is reinforcement learning. So, we will talk about unsupervised learning first and then we will get into reinforcement learning. So, what happens in unsupervised learning? We have an environment, and from the environment possibly we extract some feature vectors and we feed this to a learning system, right. A good example would be clustering algorithms in general, and the self organizing map is also an example of an unsupervised learning paradigm. Even the SWAM does clustering, but there is much more to the SWAM because there is a competitive learning mechanism within the self organizing map. So, I will kind of distinguish the SWAM against a general clustering algorithm such as the rudimentary k-means. So, if you take input patterns from the environment, they are fed into a learning system that clusters into different classes and you formulate a kind of partition on the output space, right. And this is not driven by a teacher, there is no desired response. The network automatically learns these connections, these classifications through an appropriate learning mechanism. Now, let us see the other idea, which is on reinforcement learning. So, let us see what reinforcement learning is. But before we discuss the schematic of the learning process itself, I would like to motivate with a few examples for this task. Imagine we have to train a robo with possibly 4 legs or 6 legs or 8 legs that has to navigate through an environment, a terrain environment, and there is a reward associated for this robot to take certain actions navigating through this terrain as it continuously learns from the state of the environment and takes certain actions in terms of how it has to crawl. A second example is, say, learning music from a teacher, right. So, a teacher is teaching music to me and the actions that I have to take would be to maximize my reward, and my reward would be to learning more songs in a particular music session. So, if I have to learn more songs in the session, I have to take certain optimal steps, which is I have to sing whatever I am taught pretty well, right. And this is again fed back to the environment, which is the teacher. In some cases we can also have a critique, like imagine the same learning of music example. I have a teacher teaching me music, I am learning music, and I have certain actions that I take at runtime, and there is a judge, somebody else, who is sitting and listening to this interaction between the teacher and myself and providing me some rewards as a consequence of the actions that I have taken, right. These are all examples where a learning system, in this case myself learning music, is done optimally in such a way that I maximize the reward that I can get, or expected amount of reward that I can get in the statistical sense. Okay. So, with these motivating examples, let us get into the schematic of reinforcement learning. We have an environment here. So, this environment is any environment that we can think of in the context of artificial intelligence, be it learning music, being the terrain or navigation problem, or be it maybe a child learning the environment by sampling things around what he or she sees. The state of the environment is ST, which is given to the critic as well as the learning system. So, there could be other environmental variables which are also fed to the critic, and we call this as the primary reinforcement signal. The critic in this case could be a judge which sees the environment, and there is a reward that the critic gives to the learning system, which is an agent which performs certain actions according to some optimal policy pi, so as to maximize the reward. So, in this process, so this action AT+1 happens that maximizes the rewards, and then the environmental state would be changed via this state ST+1. So, this state ST+1 which is going to be changed is fed back into the environment, and this gets reinforced back and forth. So, there is a learning through an input output mapping through continued interactions with the environment, right. In this case, the environment can be the music teacher, that is the state is changing at every time small t, right. ST, you have from t going from 0 to some capital T, you have these states available, and this agent is this agent which is learning music, and the actions it takes is guided through a reward that it sees through a critic, and the goal would be to maximize the expected rewards, right, as a function of time t, and as a consequence of it, it takes an action AT+1 that is optimal so as to maximize the reward. So, and this reward action kind of system, reward action and state, reward action and the state are dynamically changing, and this happens through continued interactions with the environment, and this is how learning happens, and this is the other mode of learning, which is reinforcement learning. And often the optimal decisions can be very well mathematically formulated using Markov decision processes and other things, other stochastic processes ideas, depending upon the kind of random process that we are dealing with as a function of time. Okay. So, this completes the details regarding reinforcement learning. So, hopefully with this you can set up interesting gaming problems, etc., that you could build using reinforcement learning topics, and this topic itself can be dealt in greater detail as a separate course. Now, let us see what learning tasks can be. This is akin to what we see in biological systems within our brain, right. One of them is pattern association. Next is pattern recognition. The other is functional approximation. Control, and many others, and typically most of the AI problems come one way or the other, they fall into one of these 4 categories. There are other categories for learning as well. So, let us see what these learning tasks are qualitatively, and as we get through the algorithms we will see the quantitative feel of what we are talking about. The first thing is pattern association. An associative memory is a brain-like distributed memory, and what happens here is you learn through associations. So, what we mean by learning through associations, we repeatedly feed an input to a network and the network learns this, and there is a storage phase and then there is a recall phase, and when I give a stimulus which is similar to the input, it provides and evokes a response which is what it has learned during the learning process, right. So, let us see what 2 modes are. One is auto association, and this auto association is unsupervised. The other is hetero association, and this is typically supervised. Now, if you describe this in terms of a mapping, there is a stimulus xk, and then you have a memorized pattern yk which corresponds to this stimulus xk, right. K is that pattern and there is a mapping from xk to yk, and this is basically the storage phase. There is also a recall phase, and in the recall phase I present a noisy version of the stimulus, right. It is not exactly xk that I learned, but it is a noisy version of xk, and I want to maximize over all memorized patterns this noisy version that I am presenting to the network, right. This is the stimulus which is a noisy version than what I learnt, and then I have learnt it through a network, and this is my network, and now I present this and it has to obtain the memorized pattern, it has to get back what yk is, right. So, this is auto association. So, the small note, I think I just made a small typo here. I wrote f, I used the same mapping f earlier. So, if you have a different function during the recall phase, you can have it as phi, right. You may be looking at that objective during recall and basically you want to maximize over that objective phi to look at all the memorized patterns and give you a pattern which is closest to the noisy stimulus.